Hello and welcome back. On last video, we defined what a metric space was. And in this video, we will define convergence and continuity for metric spaces. And we will give an example or two. We'll start with convergence first. You probably already know what it means for a sequence of real numbers to converge to a real number. And that was probably one of the first things you did in your first analysis course. Anyway, now we are going to give you the same definition, which will just be applicable to more general metric spaces. Anyway, suppose you have a sequence, say xn, a sequence of some elements of our metric space, where x comma d is a metric space, be a metric space. And we have your sequence, and our element x is an element of x. So what does it mean for a sequence of elements of metric space to converge to another element of the same metric space? So we say this sequence converges to this element x if it's the same definition. For all epsilon greater than 0, there exists a natural number such that for any element bigger than that natural number, we have the distance between xn and x is less than epsilon. It is basically the same definition as that of real sequence converging to a real number. We're just replacing the absolute value of the difference with this distance function that we have in the metric. Do you remember the discrete metric space? A discrete metric space was any set with a discrete metric where distance between any 2 points was equal to 1 if A is not equal to B, and 0 otherwise. So the question is, on this discrete metric space, what does convergence look like? What kind of sequences converge and what kind of sequences don't converge? So for example, if we have real number r with D is the discrete metric space, does this sequence converge to 1? 0.9, 0.99, 0.999, 0.9999, and goes on forever, like more and more nines. Does this sequence converge to 1? So this is your xn. Does xn tend to 1? I'll give you a few seconds to pause the video. Okay, and the answer is no, this does not. Answer is no. And the reason is as follows. So we have xn is as follows, and x is equal to 1, right? And does this converge to 1? The thing is, so the distance between your xn and x, which is your distance between xn and 1, and remember how this discrete metric is defined. It just says if A is not equal to B, then the distance is 1, is 0 otherwise. The thing is, no element in this sequence is equal to 1. Yes, they get closer and closer to 1 in a traditional sense, but in this new sense, none of them is actually equal to 1. The distance is always equal to 1. So if you choose your epsilon to be 0.5, then no matter what element you choose in your sequence, you will never get d of xn comma x to be less than epsilon. So this will never happen. Never happen. So this one does not converge to 1. And the only convergent sequences are those sequences that are eventually constant. Eventually constant sequences. Okay, so that's our convergence. Let's look at continuity. So we say for continuity we need a function, right? So let our metric space be m comma dm, where this dm is the metric space, is a distance function on our set m, and be metric spaces. Now we say let's look at continuity at a point. P belongs to m. We say f from m to m is continuous at P. How do you spell continuous? It's continuous at P if it's the same definition. If for all epsilon greater than 0 there exists delta greater than 0, well, we just replace absolute values by distance function. So the distance in our set M between, say, this P and some other point, say x, is less than delta, implies the distance in M of f of P and f of x is less than epsilon. So that will be continuous at the point P, and we say it is continuous, a function is continuous, f is continuous, if it is continuous everywhere. If it is at every point. Okay, that's our definition of continuous. I will give you an example of a like if you just choose both m and n to be real numbers and the distance to be the absolute value function of the difference, then you know a lot of continuous functions. But I will give you an example that you probably don't know. So let d, comma d, d. So let d be a set and dd be the discrete metric on this set. And suppose you have some m, comma dm to be any other random metric space. And suppose you have a function f that goes from d to m. And this f can be any function you like. It can be any function whatsoever. Can you prove that this function is always continuous? Okay, hope you had a go. Okay, let's try to prove that this function is continuous without any information on our function f. So let P belongs to this discrete metric space. Now we want to show that this function is be arbitrary. Now we want to show this function f is continuous at this point P. But since this P was arbitrary, it should be true for any P we choose. So it should be true for all P, so that our function will be continuous everywhere. Okay, let epsilon greater than 0. Now we want to show that we can find delta and everything's happen. Okay, so choose delta to be equal to, say, 0.5, to be half. And then we claim that whenever the distance between our P and some random point x is less than delta, then our f of P and f of x, the distance will be less than epsilon, like no matter what epsilon we choose. And here's how it works. So because d is the discrete metric, right? So equals 0.5, but discrete metric can only be 0 or 1. So what this means is that distance because it is 0.5 is less than 1, it actually means this is equal to 0. And that means p is equal to x. Now we want to show that the distance in M of f of p and f of x is less than epsilon, right? Now, is this less than epsilon? Well, because p equals x, we are actually computing the distance between f of p with itself, which is equal to 0. And since epsilon was bigger than 0, this will be less than epsilon. So therefore, our function, any function that goes from discrete metric space to any other metric space, is continuous. Okay, hope you enjoyed this video. I will give you more definitions of continuity and then show they are equivalent in the future video.